right, so this is number, let me make sure this is 16. Yes, this is number 16. All right, so, move that. All right, so number 16 says calculate the kinetic energy of the impact of a 15,000 kilogram object, like a comet or an asteroid, hitting the Earth. It'd be a pretty small asteroid, just to let you know, at 40 kilometers per second. Express your answer in kilotons of TNT. Use the conversion that 1 kiloton is 4 times 10 to the 12th joules. All right. Be sure to convert kilometers per second to meters per second. All right. So let's do that right away. Actually, let me write the equation first of all. So the kinetic energy. This is an equation from physics. You might have seen this before. Is 1/2. If you haven't, it's not that hard. 1/2 the mass times the velocity squared. All right. So just to let you know, the kinetic energy is in units called joules. Joules of energy. The mass has to be in kilograms, and the velocity has to be in meters per second. So that's why we have to convert this velocity. All right, so our velocity is 40, kilometers per second, which is very typical. All right, so 40 kilometers per second, and we know that in 1 kilometer there are 1,000 meters. Right, 1,000 meters. So the kilometers cancel. So it'd be 40,000 meters per second. So now we have everything we need, right? Because the mass is 15,000 kilograms. All right. So here we go. All right. And then we have one last conversion to do. So it's going to be 1/2 times 15,000, right? 15,000. All right. That's kilograms, times 40,000 meters per second, 40,000, but you have to square that. That's really where where all the energy comes from. Is you increase the mass, and the energy goes up as the square. I'm sorry, you increase the velocity, the energy goes up as the square of the velocity. So this is going to be an enormous amount of energy. And then what we do is we say, all right, well, whatever this turns out to be, it's going to be in joules. Then we're going to divide it by, the fact that 1 kiloton. So if you had 1,000 tons of TNT, right? This is a very typical value. 1,000 kilotons of TNT. Is equivalent to 4 times 10 to the 12th joules. By the way, that would be, you could say that as 4 trillion joules. Just we usually stay away from that in the sciences, but you could certainly say that. All right, so anyhow, here, let's do this next problem. All right, so it's really simple. So it's going to be 15,000 divided by 2. Right, there's the divided by 2 part. All right, and then we're going to say times. So it's going to be 40,000. 1, 2, 3, 4. Okay, so 40,000, but you got to square that. And so this is going to be, that's an enormous amount of energy. All right, so there's 1, 2, 3, 1, 2, 3. So that there's 6, 9, 12. All right, so it would be the answer would be 1.2 times 10 to the 13th joules, right? That's a J, joules. But of course, 1 kiloton, and that's the way you write it, is roughly 4 times 10 to the 12th joules. All right, so the joules will cancel, and so you just take this number, which is in my calculator already, and we're going to divide it by 4 times 10 to the 12th. So that'll give us the number of kilotons of this particular collision, right? So it's in terms of, this is the amount of energy that would come from this. So it would be 3 kilotons, right? So the answer here would be 3 kilotons. It's kilotons of TNT, right? But you just say kilotons. That's fine. Anyhow, I'll put the of TNT. All right. So all right. Let's work on the next problem, which is very similar. This one's again, it's ultimately it's going to come down to the kinetic energy is equal to 1/2 mv squared, the mass times the velocity squared. All right, but it's a little more complicated than that because you're not given the mass directly. All right, so anyhow, we have to figure out the mass. All right, so that's what I'm going to do right now, which we're going to work on figuring out the mass. All right, so it tells us that this is number 16. Around 66 million years ago, right? This is the end of the dinosaurs, by the way. An object, likely an asteroid, hit the Earth, and we can actually estimate that it was traveling at about 20 kilometers per second. That's a very good estimate of the speed. It is estimated to have a diameter of 10 kilometers. If it was composed of rock and kind of a rocky metal mixture with a density of 4, what would its mass have been in kilograms? All right, so express your answer in scientific notation, and then how many millions of megatons? All right, where 1 megaton is 4 times 10 to the 15th joules. Right, so the last one we talked about kilotons. This is going to be a devastating collision. That there's never been a hydrogen bomb that has been this powerful, as you're going to see. All right. So the main thing here is let's figure out the mass first. All right. Well, the velocity is pretty. Here, I'll do the velocity first. So it's not 20 kilometers per second. It's going to be 20,000 meters per second. All right. So remember, we're going to square that. All right. So that's good to go. That's going to go right here. All right. But the mass takes a little bit more work. All right. So you might remember, and this is written on the sample problem. The mass. Remember, you got this thing that says density is mass divided by volume. Right. So mass is going to be the density times the volume. Right. So now they give us the density. It's 4 grams per cubic centimeter. All right. So that's fine. But what about the volume? All right. So the volume, if this thing is spherical and it's round, all right. So let me do this up here. So if the radius of this thing is 5, right, half the diameter is 5 kilometers, right? Do you remember when you convert one kilometer is 10 to the 5th centimeters, all right? So the kilometers cancel, and so in other words, if you remember the volume, here, let me write the volume equation as well. The volume, and this is all in our sample problems, in the formula sheet, I should say. The volume of any spherical object is 4 times pi divided by 3 times the radius to the 3rd power. But in this case, it's going to be it'll be 5 times 10 to the 5th. But we have to raise that to the 3rd because we have to get it in centimeters so that it'll cancel this centimeters cubed right here. So whatever this number is, we're going to multiply that by 4. All right, so let's figure out what that number is. All right, and here we go. Okay, so all right, so it's going to be 5 times 10 to the 5th, all right, raised to the 3rd, All right, so 5 times 10 to the fifth raised to the third, and then times, so that's a huge number, 4 pi, 4 times pi divided by 3 equals. All right, so that's the volume. Right, this is this incredibly large. Let's see, the decimal point's right here. So this is going to be something. Let's see, 1, 2, 3, 1, 2, 3, 12, 15, 6. So something like 5.23 times 10 to the, what did I say, 13th, something like that. Right, so whatever you got to multiply this by 4. Okay, so here, this is going to be, shoot, let's see, shoot. Where is it? There it is. 1, 2, 3, 1, 2, 3. There's 6. There's 12. There's 15. 16. So it's going to be 5 point, whatever it is, 2, 3, 2, 3. Oh man, I already forgot what the number. 5.224. Like if you round it up, I'm going to use the unrounded version. Times 10 to the, what was it again? Let's see, 6. I'm trying to go too fast. 12, 15, 16, 17 times 10 to the 17th, right? E17, E17, right? And that's, of course, centimeters cubed. Centimeters cubed will cancel. So just you multiply this number that's in your calculator already times 4, right? That's the point, right? So times 4, right? Because that's the density, that's the estimated density of this this asteroid. All right, so there it is. All right, and so that's the mass. Right, if you once you let's see, what's this going to be? This. I wish this calculator would do this in scientific notation. So 1, 2, 3. There's decimals right here. 6, 12. 6, 12. 15, 8. So it's like 2 times 10 to the 18th. Is this something like that, right? I'm going to use this exact number. So it's about 2 times 10 to the 18th grams. Right now, here's the other thing: is I got to change that from grams to kilograms. So there's 1,000 grams in 1 kilogram. All right, so the grams will cancel. So I just take this number that's already in my calculator. If I can find my calculator, there it is, and divide it by 1,000. All right, so that'll change it into kilograms. All right, so now, then of course, so I'm going to do this formula, right? So this here, I guess I should write the number. All right, so it's going to be 1, 2, 3. So there's 6. There's 12. So 2 times 10, roughly. So approximately 2 times 10 to the 15th kilograms. All right, so the kinetic energy, here, let's write this out. The kinetic energy, I'm running out of time, is going to be 1/2, roughly 2 times 10 to the 15th times 20,000 squared. 20,000 squared. All right, and that's going to be the answer in joules. All right, so then we're going to divide it by 1 megaton. All right, 1 million tons of TNT. All right, so here we go. Here, let me pause it. All right, so so I put all this in. Don't forget to square the 20,000. You get approximately. So this is a huge number. All right, so I gotta finish this quickly. And then this number of joules. So 4.19 roughly times 10 to the 23rd joules. That's what this number is. Divide that by, where is it? 4 times 10 to the 15th. All right, so this will be the number of megatons. All right, so it turns out to be about 104.7. Let's see, how do I express your answer in scientific notation? All right, so it should be, it's just, here's, let me pause. The video is almost over. So it's about 104 million 104.7 million megatons.